Have you ever wondered how we can see things that are miles and miles away, completely hidden by darkness or thick clouds? Well, the answer is this amazing technology that basically acts as a powerful extension of our own senses. It's a way of seeing the unseen. Today, we're going to dive into the incredible tool that makes it all possible: radar.
I mean, really think about it. How do we precisely locate an object we can't possibly see with our own eyes? It could be a massive storm system brewing way over the horizon, or an aircraft flying right through a solid bank of clouds. The answer lies in a technology that literally turns radio waves into sight.
And you know, it all starts with the name itself. Radar is actually an acronym, one that was coined way back in the 1940s, and it perfectly describes what it does: radio detection and ranging. It uses radio waves to first detect that something is out there, and then it calculates its distance, or its range. Simple as that.
Okay, so how does it actually work? Well, the core principle is surprisingly simple. In fact, it's based on something we've all experienced: an echo.
Just imagine you're standing at the edge of a huge canyon and you shout. A few seconds later, you hear your own voice bounce right back at you. Now, if you timed how long that echo took to return, you could get a pretty good idea of how far away the other side is. Radar does the exact same thing, just with incredible, superhuman speed and precision.
So here's the basic rundown. First, the radar system transmits a really powerful short pulse of radio energy. That pulse then travels out at the speed of light. It hits an object, say an airplane, and a tiny fraction of that energy bounces back as an echo. The system then measures the total round-trip time, and because the speed of light is a constant, it can calculate the distance with unbelievable accuracy. The timing is just mind-boggling. That round trip takes a mere 12.36 microseconds for every single mile of distance. That insane precision is the real secret to radar's power.
All right, so we get the principle, but what's the actual hardware that makes it all happen? Let's take a look inside the so-called black box and see the essential components that bring this whole echo thing to life.
Now, this diagram here is basically a roadmap. At first glance, yeah, it might seem a little complex, but it really just boils down to a few key players that are all working together in perfect time. We're going to focus on the four most important parts of this whole setup. So first up, you have the transmitter. This is the powerhouse, the part that creates that big initial pulse of energy. Next, the antenna acts as both the mouth and the ears. It sends that pulse out into the world and then listens for that faint little echo to come back. Then you have the receiver, which is incredibly sensitive, and it's designed to detect and amplify that super weak echo. And finally, linking them all together is the real unsung hero of the system, the duplexer.
The duplexer's job is, well, it's absolutely critical. Think of it like the system's traffic cop. When the transmitter fires its super high-power pulse, the duplexer connects it to the antenna, but at the same exact time, it puts up a shield to protect the extremely sensitive receiver. If it didn't do that, that powerful pulse would instantly fry the receiver. Poof, gone. Then, in just a fraction of a second, it flips, connecting the antenna to the receiver so it can listen for the echo, while blocking the transmitter. It's this brilliant little high-speed switch that makes the entire system possible.
And this right here, this illustrates a huge engineering decision in any radar design. See, to get a nice, focused beam of energy, the antenna size is directly related to the radio frequency you're using. At a low VHF frequency, you would need an antenna over 800 meters wide to get a sharp beam. That's absurdly impractical. But by using a much higher frequency, like in the K-band, you can get that same exact focus with an antenna that's only 30 centimeters across. This is exactly why modern radar uses microwaves. It lets you build powerful, yet totally practical systems.
But even when you have all the right components and the perfect frequency, radar engineers face this one monumental challenge. It's a fundamental law of physics that makes their job incredibly hard. You could almost call it the tyranny of distance.
So why is it so hard to detect that tiny, faint echo from a target that's really far away? What is it that makes long-range detection such an engineering nightmare?
Well, the answer is that the energy loss is it's way more severe than you might think. The signal doesn't just kind of fade away gently as it travels. No, the physics involved are much harsher than that.
Here's the kicker. The signal gets weakened by the inverse square law on its way to the target. And then, that faint little echo gets weakened by the exact same law on its journey all the way back to the antenna. So it gets hit with this brutal energy loss not once, but twice. Which brings us to this, r to the fourth power. This is the heart of the radar range equation, and it is brutal. It means that if you double the range to a target, the returning signal isn't half as strong, or even a quarter as strong. It becomes 16 times weaker. Overcoming this insane exponential drop in power is the single biggest challenge in radar design. It requires huge transmitter power and receivers with just astonishing sensitivity.
Okay, so we've managed to detect a super faint echo. Now what? How do we transform that raw electrical signal into something a human operator can actually look at and understand?
The earliest solution was something called the A-scope. It's basically a simple line graph, kind of like you'd see on an oscilloscope. The horizontal line represents distance, or range, and any vertical blip shows you the strength or amplitude of a returned echo. It's effective, for sure, for measuring range in just one direction, but it doesn't really give you a very good picture of the world around you.
The real revolution, the thing that changed everything, was the Plan Position Indicator, or PPI. Now this is the iconic sweeping green line display you've seen in a million movies. As the antenna physically rotates 360 degrees, the sweep on the screen rotates in perfect sync with it, painting this top-down map-like picture of all the targets in the area. It instantly transformed radar from just a one-dimensional measuring tool into a complete situational awareness system, a total game changer.
So, we have the echo principle. We have the hardware to make it work, and we have the displays to make it all understandable. Now, let's connect all of that to the real world and see what the payoff is for all this incredible technology.
Radar's impact is, well, it's simply everywhere. It's the absolute backbone of air traffic control, safely guiding thousands of flights every single day. It's how meteorologists track storms and give us our weather forecasts. It's in new cars, powering those collision avoidance systems. It's used for marine and air navigation, for military surveillance, for tracking satellites way out in space, and even for peering deep underground to find lost ruins in archaeology. It is truly one of the hidden technologies that makes our modern world function.
And this technology is constantly evolving. It's getting smaller, more powerful, and a whole lot smarter. You know, it started by letting us see an airplane in the clouds, and now it helps a car see a pedestrian in the dark. So the real question for the future is this. As we continue to perfect this electronic echo, what's the next great unknown that it will finally allow us to see?